So, today we're going to do something impossible. We're not launching into space. We're going the other way. We're taking a journey to the center of the Earth. I mean, really think about it. We walk around on this planet every single day. But have you ever just wondered what's actually under all of it? Beneath the cities, the mountains, the oceans, there's this whole other world down there. So let's peel back the layers and see what's really going on. And this quote right here, it just nails it. Think about that for a second. Our entire world, everything we know, is built on a layer that's as fragile as an eggshell. It's this thin, brittle skin protecting us from this incredibly powerful interior. So our first stop is that very shell, the crust. This is the part we know best, but, it's got a few surprises up its sleeve. Okay, so here we are, on the crust. It feels pretty solid, doesn't it? Permanent, even. But compared to where we're going, it's almost paper thin. In fact, everything humanity has ever built, ever done, has happened on a layer that makes up just 1% of the Earth's total volume. Just 1%. Now, this is where it gets really interesting, because there isn't just one kind of crust. The ground under our feet, the continental crust, that's the thick stuff. We're talking an average of 30 kilometers thick, and it can even get up to 70 kilometers thick under huge mountain ranges. But the crust under the oceans, totally different story. It's much, much thinner, only about 5 kilometers, and a whole lot heavier. And that difference in weight, well, it changes everything. The lighter continental crust basically floats higher on the layers underneath it. It's why we have continents in deep ocean basins in the first place. And this difference is so important, scientists even gave them their own names. First up, the continental crust. We call this CAL, and it's a really simple name, actually. It just comes from its two main ingredients, Ca for silica and Al for aluminum. Pretty straightforward, right? And what about the oceanic crust? Well, that's called SiMa. Again, it's named for what it's made of, Sila for silicon and Ma for magnesium. So that one little switch, swapping aluminum for magnesium, is what makes the ocean floor so much denser. So where does the crust actually end? Well, scientists found this distinct boundary deep underground where earthquake waves suddenly change speed. It's called the Mohorovičić discontinuity. Yeah, it's a mouthful, so let's just call it the MOHO for short. And we are about to cross it. And just like that, we've crossed the MOHO. We are officially leaving the crust behind us. Welcome to the Earth's engine room, the mantle. The scale down here is just staggering. The mantle is about 2,900 kilometers thick. To put that in perspective, that's like driving from New York City all the way to Denver, but straight down. And the heat is, well, it's almost unimaginable. We're talking temperatures up to 2,200 degrees Celsius. That's more than hot enough to melt rock, which, surprise, is exactly what's happening all around us. But this isn't a liquid ocean of lava. It's not quite solid, not quite liquid. The best way to think about it is like thick, hot asphalt that can slowly flow over millions of years. And get this single layer makes up a whopping 83% of our planet's entire volume. It's huge. Now, this upper part of the mantle is incredibly important. It's called the asthenosphere, which basically means weak sphere, and for good reason. This is the gooey, flowing part of the mantle. It's the source of all magma for volcanoes, and it's the engine that literally drives our continents across the face of the Earth. So how does it do that? Well, picture a giant pot of water boiling in super, super slow motion. These huge churning convection currents are what supply the energy for almost every major geological event we experience up on the surface, from the sudden shock of an earthquake, to a volcanic eruption, to the slow, relentless drift of the continents themselves. Okay, we've passed through the brittle crust and the flowing mantle. Now it's time for the final leg of our expedition, the journey to the very core of the Earth. Now, the core isn't just one uniform sphere. It's actually made of two distinct parts. There's a churning, liquid outer core surrounding a solid inner core. And yep, you heard that right. The very center of our planet, despite being the hottest part, is completely solid. How wild is that? And there it is, the end of our journey. Over 6,300 kilometers from where we started, we have officially arrived at the heart of our world. And just like the crust, the core gets a name from what it's made of. It's called knife. Again, super simple. Ni for nickel and Fe for iron, or ferrous. You might also hear it called the bariosphere, which is just a fancy way of saying heavy metallic rocks. This brings us back to that fascinating puzzle. If the core is the hottest part of the planet, why on earth is the inner core solid? The answer is one word: pressure. The weight of the entire planet, the crust, the mantle, the outer core, it's all pressing down on this one spot with a force that is just unimaginable. This pressure is so great that it literally squeezes the iron and nickel atoms together so tightly that they can't melt, forcing them to stay in a solid state. So let's zoom out. Let's pull back from the very center and put our entire incredible journey into perspective and look at the whole picture. So let's just quickly recap. We started on that thin, solid crust made of Sile and Sema. We descended through the vast, semi-solid mantle. We plunged into the liquid outer core of Knifey and finally reached that solid inner core, also Knifey, held in that solid state by immense pressure. Each layer is its own separate world, with its own depth, its own physical state, and its own chemistry. You know, our journey to the center of the Earth has really shown us one big thing. We live on an incredibly active and dynamic planet. The ground beneath our feet isn't static. It's constantly being shaped by all this incredible heat and pressure from deep within. The world we see today is really just a snapshot in time. The real question is, what will these deep forces shape our world into next?